Thank you very much, Kyle. I want to thank the organizers for giving me this opportunity, but you realize that it's a big challenge that they've given me to say anything coherent about the enormous work that Doug has done. So I decided that I really wouldn't try to do that and focus instead on the early part of his work that I had something to do with. There's various justifications for that, I think. One is that 10 years ago, it's hard to believe it's that long, Mike, who's just appeared here out of the clouds, gave a beautiful talk in Baltimore on Doug's work, which is recorded verbatim as part of the published account of that conference. So I can't match his wit and wisdom that you'll find there, and obscure jokes about big round orange heads and things like that. And also, of course, Doug's work is so permeates to homotopy theory as it's done today. There's really no need to review it for you. You're all embedded in it in everyday work. But so let me talk about some of the older things here. So this has been great fun for me to review, to remember those old days. So here's Doug's vita. You can see he was in a hurry. He was hired by MIT after 2 years of graduate work. Then went on to Columbia University, and the story that I'll tell actually picks up after he'd moved to Columbia, and especially when he moved to the Princeton area at the Institute for Advanced Study in 1974. You can also see that he hasn't shied away from the administrative part of this profession of ours. So let's see. Princeton 1973 to 75 is the era that I want to focus on. There's Doug in his twisted topology cap. Already on location there was Steve Wilson. Steve was a graduate student of Frank Peterson's, and so Doug and Steve overlapped for a year at MIT. Steve came to Princeton in 1972. At that time, I was a beginning third-year graduate student. I was looking for a thesis project. I had no idea, really, of what to do, and Steve came filled with ideas, and so my career was directed towards BP and so on from Steve's influence. So in this era, we had other supporting actors. Jack Morava. Jack returned to the U.S. around January 1973 from time in Russia and India, and so he came to the Institute for Advanced Study in January 1973, and he was there for a year and a half and was a big player, a big supporting. He supported us, and there were other people around too. Peter Landweber at Rutgers was we looked up to him. He was the éminence grise of this co-bordism thing, even though when you look at it, he was just like 5 years older than we were, but he seemed infinitely knowledgeable. And also I want to mention John Moore, who supported the homotopy theory activities at Princeton and conducted seminars and things like that. He was a generally supporting character. Now, some of these pictures aren't actually from the era that I'm talking about. So Steve, it's hard to find youthful pictures of. I think he's done some kind of erasing in there in the web. But here's a picture of Doug from roughly that era. And to really get a sense of what this age of Aquarius was like, you have to look at the Wikipedia page for Jack. This is on Wikipedia. So what was happening? So the first thing that happened was, so Doug was at Columbia at this time. In the fall of 1973, we founded the Bording School, and this was a series of lectures mainly by Jack at Princeton. And you can see the list of topics there sort of covers the field as we still use it. It was, this is the background. And he brought a lot of this into play. He brought the deformation theory. He introduced us to Lazard's work. He had his own description of Landwehr-Novikov algebra. He told us about Morava K theories, which he constructed using Sullivan's theory of manifolds with singularities. So this was a seminar that happened in the fall of '73. So just a word about what the mathematical cast of characters were. So we were concerned with the Brown-Peterson spectrum. This is a p local factor of complex bordism. And we thought it was very convenient because it had a very much smaller set of generators in these dimensions, twice p to the n minus 1. We were going to be interested in the atom spectral sequence. Rafe Zoller, also at Rutgers, had been making computations in the atom's Novikov spectral sequence, but using BP co-operations. And this is a topological algebra, and you have to remember the topology. And this seemed like a kind of hard road to go down. And so we had Frank Adams's co-operation approach, very recently published approach to work with, and we decided to work with that. And we had a start on a computation of the atom's Novikov E2 term of the X over this co-operation algebra in the form of this theorem of Peter Landweber and Jack Morava's that identified what the only invariant ideals, prime ideals are in BP stars. So these are, well, I was wondering if you could, Doug. Any guesses? I don't know how clear this picture is. Shall I tell you? That's Bill Browder. Yeah, okay, so there are more people there. Right, so we had a beginning computation of X groups in the form of this prime ideal, invariant prime ideal theorem. So after that boarding school, oh yeah, let me also bring out the target of this. In the air was the beginning of periodic families of homotopy classes. I think Frank Adams called them systematic elements in stable homotopy of spheres. They were the first time they appeared was in work of Toda, where an application of Toda brackets. Toda was really not interested in systematic phenomena. He was a stem by stem guy, and at that point, and he constructed elements alpha t, but he didn't care too much about their indeterminacy, and he didn't know or really care whether they were non-zero in large dimensions. So there's Toda on the left. Some of these pictures, by the way, come from talks of Doug's as well. He's been a great collector of the history of this subject as well. So it was Adams channeling Michael Barrett, I think, who published the idea of looking at self-maps of finite complexes and producing systematic elements in homotopy groups of spheres by coming in on the bottom cell, mapping by an iterate of the self-map, and coming out on the top cell. And so Adams did this and variants of this. And he acknowledges influence of Michael Barrett. I think Michael had this construction. In 1969, Larry Smith applied complex bordism to this problem. This was the introduction of complex bordism to the question of periodic of families of elements. He gave names to the sequence of finite complexes. V0 is the Moore spectrum. V1 is the cone on the atom self-map. And he constructed the next in this family. He was led to the notion that there would be a next one by the structure of MU. And so he constructed a new systematic family of elements, this beta sub T family. And he could prove that they were non-zero by using complex bordism. In his paper, he expresses a lot of frustration at how hard this was and at the fact that he seemed to have stopped at this point. Why aren't there lots more VNs? The pattern is clear. Why can't we just construct them systematically? Well, in 1970, Toda reproduced Smith's construction and gave bad news that you often couldn't make this kind of construction. But he also constructed another one, a self-map of V2, Larry's new 8-cell complex V2, and therefore constructed a whole new family of a systematic family of homotopy classes, these gamma sub T elements. So, and he knew that the gamma was non-nilpotent. It's injective in MU and in MU homology, and so it's definitely non-nilpotent. But he didn't know whether any of the gamma T's were essential or not. Toda didn't know at this point whether any of the gamma T's, even gamma 1, even the first of these things, he knew the homotopy group that it lay in. He knew that it was of order P generated by that class, but he didn't know whether gamma 1 was 0 or not in that class, in that group. Well, the next year he published a paper which showed that it was 0 in that group. And that was cool until the next year after that, Zahler and Thomas published a proof that it was non-zero. And in their paper, they explained that they've exchanged proofs with Oka and Toda and no serious gap has been found in either. Now, I'm just trying to put myself in the mind of the editor who accepted a paper like this. I'm not sure it happened today. But there it was. This was a big deal in the era. It was picked up by Gina Colada, who's a science reporter for the New York Times and other people, and she wrote an article in Science that was very widely read that wondered whether this math venture was really going off the tracks, and it was much better to just accept probabilistic arguments. After all, these arguments were getting so complicated, nobody could really understand them. Well, luckily, a few years later, Oka and Toda came around and agreed that gamma 1 was actually non-zero. And as time went on, the proofs of these things got simpler. All right, so that presented a challenge to us. And this is where Doug entered the picture. In the fall of 1974, we decided to pick up this challenge, Steve and Doug and I. Well, actually, let me step back a little bit. Here was the challenge in 1973. These things existed. We could construct. It's easy to construct Greek letter elements in Ext by looking at these short exact sequences and taking and iterating the boundary homomorphism. The question, and once you've constructed the geometric self-map, then the question of whether the gamma elements and so on were non-zero or not, that's a completely algebraic question. It's just a question of whether the iterated boundary of the Vn to the t is 0 or not. So this was the challenge that was clear to Steve and everyone. And so in 73 and 74, Steve and I sat down to try to address some of that, and we computed X1 with coefficients in this BP star mod IN, this cyclic comodule. And so the case I want to focus on is when n is 1. So I'm looking at X. Not sure I have the numbers right. Yeah, I'm looking at X1 from BP star into BP star mod P. So we produce elements there by taking the boundary of powers of V2, and that generates the kernel of V1 by the long exact sequence. So the only question really was we have to identify where the torsion-free component is. That was pretty easy in this case. And we have to figure out what how divisible this boundary, this boundary of V2, V2 to the T is. And we came up with this number, which a little bit complicated, and the divisibility beyond V1 to the P to the K, that was surprising. That was unexpected. When n is larger, the formula is more complicated. But this was the picture then. And so by taking the boundary on these new elements in X1 mod P, taking the boundary of them in X for BP star, we could produce generators for the kernel of multiplication by P in X2. And so these give you a whole family of classes in X2 that came to be called beta T slash J, where you've divided by V1 to the J. Okay, so that was work that Steve and I had done. And then in the fall of '74, so I remember in the spring of '74, Steve and I had been working away, and at some point Steve took me aside and said, Doug is coming to the Institute, Doug Ravenel is coming to the Institute next year, and I would like to include him in our project. Things will change. Doug is very smart. So Steve is rarely wrong about things, and he certainly wasn't wrong in this instant. Things did change. So here was the way this project with Doug unfolded. So we were aiming for the gamma T's. They were the controversial guys. Let's just think of a simple situation. You've got this short exact sequence where I multiply by P by power of P, and that gives me a boundary map which produces these elements in X1 for BP that turn out to be generators if the prime is bigger than 2. And so thinking about multiplication by P to a power was important. And Doug came up with the idea that we should embed all of these short exact sequences into a single kind of universal example, where you just take BP star and embed it into its localization by inverting P, the prime P. And the quotient, we wrote BP star mod P infinity. And then this element, this generator in X1 can be written as delta as the boundary of a fraction. And so fractions, fractional elements like this made an appearance there. I remember in October, November 1974, all of a sudden we were talking about fractions. And of course, this torsion comodule, BP star mod P infinity, is a union of BP star mod P to the K's, and each one of them admits a power of V1 as a comodule self-map. And so you've got a kind of end periodic thing happening here, and you can invert V1 on that and get another comodule. And so this this simple picture embedded into a whole resolution, a whole complex. This is the chromatic complex and the chromatic resolution. And when I apply X from BP star into this, I get a spectral sequence converging to the E2 term for the sphere, the Novikov E2 term for the sphere. So this was cool. It really put everything into a lot of these computations into a single framework. The question, of course, was how do you compute this E1 term? This is pretty complicated. It's got torsion with respect to these first family of generators. But when I say we, I really mean Doug, realized that you could address this by a series of Bachstein spectral sequences, and in the end reduce the question to computing X of this V1 inverse of BP star mod IS. So you kill the first S generators. And we had Jack here who told us what the answer was. He related this to the cohomology of the Morava stabilizers, as we say now, and linked that with Michel Lazard's work. And you find this amazing result that the E1 term in the chromatic spectral sequence has this bound, and this said that in in the chromatic spectral sequence itself. This is the E1 term of the chromatic spectral sequence. The spectral sequence is concentrated under a parabola that's pierced by spikes of sort of Kroll dimension 1 cohomology every p minus 1 columns. So this was tremendously exciting because it seems that if you're interested in n less than p minus 1, this is a finite calculation. There's something that we might actually be able to completely compute. Well, so here's a picture of what the chromatic spectral sequence looked like in the very beginning of it. So the elements of Barrett and Adams appear there, right here. I mean, there was unfortunately in this corner there was a copy of the rational numbers, and we know that's not what the zero stem is. But luckily, there's a differential in the chromatic spectral sequence that maps out to z mod p infinity here, and the kernel is the z locally that you want. And similarly, the other Greek letter elements appear, there's an edge homomorphism in the spectral sequence, and they appear here on the bottom row. And so we understood that in order to determine whether the gammas were non-zero or not, well, what we really had to do was completely compute this group in this position in the chromatic spectral sequence. And this would really amount to computing x2 for the sphere. So that's what we set out to do. And we did this. So at the same time, Doug was doing other calculations that I'll talk about in a minute, and could see that for large primes, this x of v2 inverse bp star mod p and v1 was a 12-dimensional vector space. And we were only computing the effect under these pair of Bachstein spectral sequences. We were computing the effect of one of those 12 generators. And we called the whole family the 12 tribes. And we had a vision that someday we'd be able to compute the whole cohomology and the effect of each one of these 12 tribes. Well, we didn't do that, but other people did later. So Shimomura and Yabe did this later. Also, by the way, we were focused on p bigger than 2. Shimomura and Steve Mitchell made this calculation for p equals 2, calculated x2 for p equals 2 independently. Steve was a graduate student of Doug's at the time. So let me just say a word about the evolution of this family of beta elements in the 2 line. So they've become really important. They have beautiful interpretations in terms of modular forms by Garrett Lauris and Mark Behrens. And we know something about the survival of those classes. X2 is a big group. We know Oka proved that using them you could construct p groups of arbitrary rank in stable homotopy. And then Halsedowski, another student of Frank Peterson's, showed that any finite p group occurred inside the homotopy group, the homotopy groups of spheres, by using these beta elements. So most of what we know is a few survival theorems and one non-survival theorem, beta p to the k, and I'll come back to that in a minute. Well, so let me return to Doug here. These were amazing years. This was an amazingly productive period. This is a list of papers that were published just around that era. Structure of Morava stabilizer algebras gave us, we're still exploiting this paper today, and the cohomology of the Morava stabilizer algebras. Meanwhile, Steve and Doug were doing an independent project that I'd like to say something about, this Hopf ring story. So let me just say a word about that. Again, this is something that's had legs. We still are looking at exactly this kind of issue. So if you look at the unstable spaces in MU, underlined, Steve's thesis showed that the homology of these things was torsion-free. And so there's a diagonal in the integral homology, and so the whole sequence of spaces provides you with a graded ring in the category of commutative coalgebras. And what Steve and Doug did was to give a complete description of this as satisfying a universal property. So they constructed some very simple classes in the homology of this, in this Hopf ring, in the homology of these unstable spaces. The homology of MU, the homotopy of MU, maps into the zero-dimensional part, the zero-dimensional homology of the negative spaces in that MU omega spectrum. And there's also the generator of the MU cohomology of CP infinity, and that produces a map from CP infinity to MU2, and so you can look at the image of the homology of CP infinity. So you get this picture that in the lineup of these even spaces, let's focus only on the even spaces, you've got the homotopy of MU moving off to the left along the bottom, and on the MU2 column, you have the homology of CP infinity. And those two families of elements generate the Hopf ring, and the only relation is an obvious relation that you can write down very simply. So this was a beautiful, beautiful result. People had thought about Hopf rings before in terms of the homology of QS0, for example. Madsen and May and Tsuchiya and people had thought about a single space, a single infinite loop space. But this was thinking of a whole graded object, and it was new territory. Right. So here's another paper. This is another piece of the chromatic story. Doug proved that in this paper dealt with the odd primary analog of the ARF invariant element. So this is given by the p-fold Massey product of the generator in dimension 1 in the classical Adams E2 term. So this was a well-known generator. This was investigated by Cartan and people, this class. And he proved that for p bigger than or equal to 5, these classes all die, except for the first one, which survives to beta 1 and doesn't die. So I just wanted to say a word about his method. Here's the theorem again. So this is a theorem about the classical Adams spectral sequence, but his method was to try to relate it to the Adams-Novikov spectral sequence, the BP-based Adams spectral sequence. So he thought about all the classes in the E2 term for BP that mapped to the element B sub I that he was interested in. One of them is this beta p to the I class, but there are possibly many others. And the objective was to show that they all die by a differential. All of them die by differentials. So that means you have to understand a lot of classes in homological dimension 2p plus 1, which is way beyond where you can make explicit calculations in the Novikov E2 term. So, but he just needed to see that certain elements were non-zero, and so he did that by mapping out to another group that he could compute, namely the cohomology of cyclic group. And so this was a beautiful application of originally ideas of Jack's, but this is really the first time that these ideas of Jack's entered to homotopy theory in a serious way. So the argument is a beautiful induction using Massey products and starting with Toda's differential. So this is really one of the great papers in the subject. Let's see. In fact, this strategy formed the model for what Mike and Doug did 35 years later in their proof of the Kervaire invariant. They tried to do the same thing at the prime 2. Things are a little more complicated, but the strategy is very much the same. Okay, let's move forward a little bit. Here's some publications from 1 year. Busy time. So Doug had his hand in the Siegel conjecture story. He proved the Siegel conjecture for cyclic groups, and therefore for S1. So this was the first time we were starting to get an idea about Siegel conjecture kinds of questions for compact Lie groups. Worked on the HP sequence. And then at the bottom, there's this paper called Localization with respect to certain periodic homology theories. So I would say this is the founding document of the whole story of chromatic homotopy theory. And if you haven't read this paper, fix that. It's very exciting paper. So what does he do in this paper? What are the things that he accomplishes in this paper? I think everybody who reads it will come out with his own response to that question. For me, one thing that he did was to show that Bouwsfield localization was actually a practical strategy, computational strategy in homotopy theory. Now, you have to realize that when Doug started to write this paper, Bouwsfield localization didn't exist. So it's amazing that, that he could do this. So he and Pete had this interaction. You can see this is a quote from Pete Bouwsfield's paper, grew out of an attempt to understand Doug Ravenel's work in the localization of spectra. So this developed hand in hand. So this was one important thing to get Bouwsfield localization into play. He focused our attention on these particular chromatic localizations that have played such an important role since then. He worked out what the K-theory localization of the sphere was, and verified one of his conjectures, that L1 is smashing. And he really set the path forward in stable homotopy theory by means of a series of conjectures that some of which he proved later, and of course most of the rest of them were proved by this triumvirate of people, where I did get fairly contemporary photographs of these guys. I think Ethan is a little older in this picture than he was then. This began, by the way, in another thesis under Frank Peterson's direction, Ethan's thesis. Okay, so let's see. More on the 1980s. So I guess the Siegel conjecture appeared twice in this list. What do you know? Doug turned out to be a physicist, a closet physicist. Who knows? Communications and mathematical physics. Now there's this last entry there, complex bordism in stable homotopy groups of spheres. So here it is. Is it the green book? How many say green and how many say red? How many say green? How many say red? Amazing. Would you have expected that? It's almost all green. It just shows how long we've had this book, all of us. So in the introduction, the preface to this book, he explains what his goal was, music of the spheres. So already we start to see eclipses and just celestial events playing a role in Doug's thinking. But he said his purpose had three purposes. He wanted to make BP theory and the Adams-Novikov spectral sequence more accessible. He wanted to provide a convenient reference, and he wanted to demonstrate the computational potential. Well, I think we can say that he succeeded in all three of these objectives. If you look at the first chapter of the book, it's got a summary of homotopy theory, which is where we all go to learn about the EHP sequence and many, many, many other parts of standard homotopy theory. Here's the table of contents of this book. The three appendices are pretty fantastic. This is the standard reference for the story of Hopf algebroids. Where else would you look to learn about formal group laws? So this is Doug's book, Doug's first book. let's see. Moving on, the 1990s. So proving some of these conjectures, the root invariant, and then work on the telescope conjecture. So a lot of Doug's effort in the 1990s had to do with the telescope conjecture. I'm not going to try to describe to you what the telescope conjecture is. It was the one part of Doug's list of conjectures that remained unproved after the attack by Devenetz, Hopkins, and Smith. And it's unsolved to this day. But I wanted to say something about Doug's approach to it because I think it's very, very interesting. So this is actually, Doug has made many attacks on this conjecture, and I just wanted to say one of them, say a word about one of them. So, so the game is to try to show that it's not true for n bigger than 1. So I had used some method to prove, originated with Novikov, actually, to verify the telescope conjecture for n equals 1. And it involved finding a way to use BP to compute differentials in the atom spectral sequence. So Doug wanted to do the same strategy, but compute differentials which would imply that the telescope conjecture is false. I used it to show that the telescope conjecture is true and then is 1. He wanted to use it to show that the telescope conjecture is false for larger n. So the game is you form the atom's filtrations of the sphere, both with respect to ordinary mod p homology and with respect to BP. So you've got these two filtrations on the sphere, and you smash them together. And so you get this double complex thing. And so then you can smash with any spectrum you want, and you get a similar double complex thing. And so one more picture on the board. So how did it go? Well, anyway, so if you filter this thing horizontally, this gives the classical atom spectral sequence. Whereas if you filter it by taking everything to the right of something, this gives rise to the E2 term for the BP spectral sequence. This was how far I'd gotten. And Doug made the point that you don't have to do that. You can actually filter this by any line of negative slope you want and take all of the stuff that's above that line of some slope, some negative slope, m. And so as you do that, you get a whole family, a whole family of filtrations, different filtrations of the zero sphere, each giving rise to a different spectral sequence that somehow interpolate between the classical atom spectral sequence and the BP atom spectral sequence. And so by carefully choosing that slope, he hoped to be able to compute differentials and get a contradiction to the telescope conjecture. So he was never able to close this loop, close this idea. But I think it's a beautiful computational strategy, and there's probably a lot of play left in this idea. Okay, Doug's the inventor of elliptic cohomology as first example of something constructed with the name elliptic cohomology due to Bob Stong and Peter Landweber and Doug. Don't have to talk about the huge play that's had. So these are two quick remarks on two amazing things that one could spend many lectures talking about by themselves. So HKR, the theory of higher characters with Nick Kuhn and Mike Hopkins. Again, something that's current to this day. Finally published in 2000 after living underground for many years. Well, what else was happening in the 2000s? Lots of work on various extensions of the Novikov E2 term, and more work about elliptic cohomology. So Doug was interested in getting higher height analogs of elliptic cohomology by using Jacobians of curves. And so I think these papers towards higher chromatic analogs, they presage the later work of Tyler Lawson and Mark Behrens on TAQ as well. A different approach to the same kind of question. Well, then there's the Kervaire invariant story. So, you know, I don't have to say anything about that because we're all so ingrained in it. Here's the guys that are doing it. So I'm not sure what this glyph means. This is part of a lecture that Doug and Mike give. I don't know. I mean, what does this mean? And the name of the title of the lecture, by the way, is Plastic Explosives. What is that about? I mean, I don't know. What? C4. Okay. Well, I was thinking about it. I thought maybe this represents the strategy of the proof. It's a convergence of these three colors. There's three components to the proof that came together in this work. The theory of structured ring spectra. Okay, Doug. Okay, I know. I know that. They combined the theory of structured ring spectra and equivariant stable homotopy theory and ideas from motivic homotopy theory in an amazing way. And my interpretation of this is it's the coming together of these three major strands of homotopy theory over the last 20 or 30 years. But it might mean other things. I mean, maybe they had this in mind. But after all, Doug is the one who saw that homotopy groups, this white noise, this complicated thing, was actually composed of monochromatic layers. So he decomposed this, just like this guy, just like Isaac Newton. And then I started to think there's actually more to this analogy between Doug and Isaac than you think at first. They both wrote books that founded subjects. Actually, they both were founding members of two major paradigms in science. Newton with his theory of gravitation and his theory of optics, and Doug with chromatic homotopy theory and the Kervaire work, the equivariant work there. It's quite a good analogy. And then there's a famous biography of Newton's called Never at Rest, and I realize this sums up my impression of Doug perfectly. He's never at rest. There's always never a conference when he's not rarely sitting in the front like this, but he's usually in the back writing down fractions. It's never a moment. So let's see. This is an Eclipse conference, isn't it? But it's not the first Eclipse conference. The first one I know of in homotopy theory was in Huastepec in Mexico in 1991. This is the glyph, the image from that conference. This was a conference in honor of Mark Mahwald's 60th birthday. And I was at that conference. I have to say, I hope this conference isn't as jinxed as that one was. I can tell you many stories of things that happened in that conference. But it was a great experience. I was looking at the preface to the proceedings of that conference, and this is what I found. That at the Adams Memorial Symposium, Doug Ravenel called our attention to the coincidence in 1991 of Mark's 60th year and an exceptionally promising total eclipse of the sun. So Doug was responsible for that eclipse conference as well as this one. Now, I have a prediction that, in 2024, in April 2024, the next total eclipse to go over the U.S., the full U.S., is going to happen. And look where it's going to go. It goes directly over the city of Rochester. He will get 3.5 minutes of totality without leaving his house. Well, it knows you're there now. So that's all I have to say. This is Happy birthday, Doug. I like this quote a lot. Happy birthday.